Welcome to this lecture. So here in this demonstration we are going to see how to implement a statistical model based logistic regression based binary classifier. To do this classification task, we are going to utilize the diabetes.csv dataset available from the Kaggle. So the first step is to import the libraries, namely pandas and numpy. And the second step is to load the dataset and manipulate the dataset. So we are going to read the CSV dataset named diabetes.csv with the help of pd.read_csv. So first let us visually inspect the information about this dataset saved in this variable named diabetes. We could see clearly there are totally 9 columns in this dataset, right from pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, to degree function, age and outcome. So now let us display visually the dataset. So .head function helps us to display the first 5 samples of our dataset. Here we can scroll towards right in order to see all the 9 different parameters of the dataset. Out of that we could see, fortunately the entire dataset has all the variables in the numerical format. There is no string information. So we could see, since this is a classification task, the last variable or the last column in this dataset named as outcome is comprising of values called as zeros and ones. So means what? 1 represents the patient is having diabetes, 0 represents the patient is not a healthy person, not having diabetes. So means what? This outcome variable is our final label. So the next step is to split the dataset into training and testing portion. So we are going to import the train_test_split function available in the sklearn library. So in this case we are going to divide our dataset into 50% of dataset belonging to test size and 50% belonging to training size. So right now the labels are not, right now the dataset is not splitted into input features and the output label separately. So entire data are available in this case. So how to understand it? You just use, so right now this variable carries training information, this variable carries the testing information or testing samples. So randomly training and testing samples are splitted, right? So these are your IDs of your samples. So random samples. So .head function displays the first 5 samples of our testing training data set. So we could see all the 9 features are displayed in this case. So the next step is to import the Statsmodels based library functions in order to prepare our logistic regression based binary classifier. So the library functions useful here are Statsmodels.api, Statsmodels.formula, Statsmodels.api as SMF and Statsmodels.formula.api input logit function, because this is a logistic regression task. The next step is to define our own formula. Right now we have 9 different variables, right? So out of the 9 different variables, outcome is a variable which is holding our final labels, either 1 or 0, to inspect whether the patient is having disease, diabetes disease or not. So this output is being framed with a formula, like outcome is approximately identified based on the input features available in our data set. So we are summating all the input features, pregnancy, glucose, blood pressure. So we are using the plus symbol with respect to all the input features. We are not omitting any input features. So this is our formula. Let me run this formula. The next step is to define our logistic regression model with the help of this logit function. So the logit function uses this formula just now we have utilized. So formula is equal to formula, and once the model is defined we can immediately do the training process. So using the .fit function we can do the training process with the help of the training data. So let us train the model here. So once the training is done, we can look into the summary of the model. So this model is statistical based model. So we could see once the model is trained, we could see the standard error of the model, coefficient of determination of the model, the z values, and the hypothesis based probability of z values and the associated label values. The next step is to display the model parameters in terms of intercept and all the other features. The next step is to import the classification metric. The most familiar and useful metric in order to identify the performance of this classifier model is accuracy score. So right now we are going to predict the model with the help of model.predict. We are going to use the test data set in order to do the testing or prediction process. Right now, once the model has been predicted, the predicted labels are stored in the variable called prediction. These prediction values are random in number, and we are going to use a cutoff variable, and we are going to assign a threshold value of 0.7. So right now, with the help of this numpy function, we are going to manipulate this prediction values, whichever the prediction value belonging to greater than this cutoff value are converted to 1, and the rest of the other values are converted to 0. So with this manipulation function, y underscore prediction stores a new value which carries only either 1 or 0 value. So let us run this function, and after that we are going to take the original label from the test data. So our original labels are available in the column named outcome. So we are going to segregate or take only the outcome or original labels available under this column from our test data set. Now y underscore actual carries original labels, y underscore prediction carries manipulated model predicted labels. So already we have imported the accuracy underscore score. So right now we can display what is the accuracy of our model. Accuracy is not defined in this case. So we have to compute accuracy, right? So this is how accuracy is calculated. So once the accuracy is computed, then we can print our accuracy. So right now for the 50% of the training and testing data set, the accuracy obtained is 77%. If suppose we are going to modify the training and test size of our data set, say for example, right now I am going to fix only 30% of our data as test size and the remaining 70% as training size. Again, we are going to fix the formula, we are going to train the model, we are going to predict the model, and then we are going to manipulate the predicted variables. We are going to take the original actual labels, compute accuracy of the model, and print the accuracy. For 50-50 percentage of trained data split, we got 77% as accuracy. But then once we reduce the test size, we have a reduced accuracy of 75% only. Thank you.